Welcome to the CBDC video series, a way for regulators, researchers, and international organizations to learn more about stablecoin technology, design, and policy considerations.
Okay, hello. So thanks for joining us again. Another edition of CBDC and Cello. For those of you who don't know me, my name is Ezekiel Kopik. I work for C Labs, which is one of the companies working on Cello, and I work with the official sector. So I'm a former central banker myself. I used to be at the Federal Reserve Bank of New York for many years before moving out west and joining Cello. So today I am going to focus my remarks on interoperability, a topic that is gaining urgency with respect to central bank digital currencies, or CBDC for short. Specifically, I want to focus on interoperability as it relates to retail CBDC. So in a recent report on retail CBDC by the Official Monetary and Financial Institutions Forum, or OMFIF as it's often called, 60% of their central bank respondents expressed concern that interoperability would encumber progress on CBDC issuance. Meanwhile, 43% admitted they are currently only focused on strictly domestic CBDC use cases. Unfortunately, as the report notes, a divergence in standards across countries could limit CBDCs from reaching their full potential. Now, there are lots of ways in thinking about interoperability, but one important aspect that I want to touch upon today is this idea of building bridges between blockchains. So in order to understand the importance of bridges, I think it's important that we take a step back and we look at Bitcoin and Ethereum. As many of you already know, Bitcoin was developed in 2009 and currently has the largest market cap of any crypto asset at $175 billion. About 6 years later, in 2015, the Ethereum blockchain was created. Although its market cap is a fraction of Bitcoin at $26 billion, it helped revolutionize the crypto space. By allowing people the ability to create decentralized applications, leveraging smart contract technology to address real-life use cases. The issue now, of course, facing the industry is that many people with Bitcoin, for example, would like to take advantage of these decentralized apps, or dApps as they're often called, on Ethereum that would then afford them this ability to utilize, for example, savings dApps or lending dApps, something like that. However, Bitcoin and Ethereum operate on two different and distinct blockchains. Thus, for a Bitcoin user to access dApps on the Ethereum blockchain, she would need to access a bridge between the two chains. But of course, this is where things can get tricky. So when bridging from one blockchain to another, there are essentially two options: a trusted or semi-trusted option and a trustless option. In the trusted version, a user essentially exchanges her Bitcoin for tokens that can be used on Ethereum. These are often referred to as ERC20 tokens, which is basically a technical standard for token implementation on Ethereum. Now, anyone using this option is implicitly relying on or trusting a small group to verify that the tokens they receive are in fact valid. So for example, there's a project called WBTC, which stands for Wrapped Bitcoin, which relies on a consortium of institutions performing different roles to essentially wrap the Bitcoin for use on Ethereum. Excuse me. Another project being developed is TBTC, which is working to allow people to use Bitcoin in Ethereum dApps by using a group of randomly selected signers to safeguard the transaction. Now, in both instances, there is some level of trust that the tokens received are, in fact, backed by the Bitcoin for which it was engaged. The second, or trustless option, does not require the user to trust anyone, as the protocol will instead verify the state of the chain to which it's connecting to ensure the accuracy and legitimacy of the transaction. So although the trusted option may work for wholesale CBDC, as the ecosystem of participants there can be rather small, it's likely that users of retail CBDC will prefer the trustless option. But there are, of course, issues associated with this option that need to be addressed. Specifically, the fact that Bitcoins have been growing steadily makes it harder and harder for resource-constrained devices to do a full sync and thus verify the state of the chain. As you can see in the chart, the Bitcoin blockchain has increased significantly in the past few years and is now more than 280 gigabytes of data. The Ethereum blockchain is even larger at approximately 340 gigabytes. So if you want to create a bridge from Bitcoin to Ethereum using a full sync, you essentially have to recreate that Bitcoin blockchain on Ethereum, which effectively doubles the size of the chain to more than 600 gigabytes. Additionally, at the same time, the number of resource-constrained devices continues to explode. So according to the Ericsson Mobility Report, released last November, there are now more than 8 billion mobile devices with an active subscription, and with close to 6 billion of these classified as smartphones. It should also be noted that the smart contracts mentioned earlier are even more resource-constrained and expensive, which means that you simply can't do that much computation, nor can you store that much data. This means that it is effectively impossible to bridge from one chain to another using a full sync. The data requirement is simply too great. However, it appears that the founder of Bitcoin, whoever that is, contemplated this very issue. So in the original Bitcoin white paper, there's a description of what's called a simple payment verification technique, which describes how light clients can sync with the chain by downloading only the headers of a chain. Assuming there is no 51% attack scenario, the simple payment verification method suggests the light client can verify that the latest header it's presented with is in fact part of the longest chain. The light client can then request transaction data from full nodes and use the latest header for verifying any Merkle proofs the full node sends with the data. Unfortunately, the amount of header data needed to sync in this fashion is still significant. For Bitcoin, it's 50 megabytes approximately, and for Ethereum, it's 5 gigabytes, which is very large. So returning to our cautionary tale, even using this simple payment verification method, there's simply too much data to create a trustless bridge between two chains. In fact, a project called BTC Relay tried to sync the Bitcoin chain on Ethereum, but the cost of maintaining this became prohibitive. In fact, the last write to the BTC Relay smart contract was almost 2 years ago. Now, this example is especially relevant for the discussion on central bank digital currencies, which we will now have. So when thinking about CBDC, there's been a lot of research done. A lot of central banks are currently working on pilots and certainly exploring the idea. But it's highly likely that for most central banks that are contemplating the issuance of CBDC, they're envisioning that it will be done on a private network, which may or may not actually include or utilize blockchain technology. So, and it's also likely that this private network is probably not going to produce a significant amount of those decentralized applications, such as the ones on Ethereum that we mentioned earlier, that provide so much utility for people. So these savings applications, these lending applications, etc. So as with Bitcoin, users of this CBDC will also desire a bridge, to public blockchains like Ethereum, where they can access these dApps. Additionally, you can also easily imagine a scenario where you would want to build a bridge between the CBDCs of two countries. So you could try and build a trusted bridge between CBDCs, and this certainly might work for a wholesale version of CBDC where the number of participants is limited. But in truth, there are probably limits to the amount of trust that exists between governments. So nonetheless, when it comes to retail CBDC, it will likely be necessary to create trustless bridges. But in order to build trustless bridges that work on resource-constrained devices, like we talked about earlier, such as the mobile phones, the smartphones, and then also utilizing smart contracts, central banks will need to ensure that the data necessary to verify transactions is as light as possible. So in order to address this problem, the team working on Celo has developed an open source light client called Plumo, which has made innovations in the use of epoch-based syncing, BLS signature aggregation, and SNARKs to reduce the amount of data necessary to verify the state of the blockchain. So now you might be wondering, where does the name Plumo come from? And Plumo in Esperanto means feather, so hence the sort of a connotation to a light client. So I'm going to explain in a little bit of detail some of the thoughts and concepts behind these three innovations, but I'm obviously not the expert when it comes to the technology side of this. But for anybody who is interested in learning more of the specifics behind each of these three, we have also produced other crowdcast videos that go much more in depth into each one of these. So I certainly would suggest reaching out, and we can be happy to direct you and point you in the right direction for more in-depth analysis of this. But for right now, I'm just going to give a very high-level overview of these three. So first, when it comes to epoch-based syncing, Plumo introduced this concept of epochs. And essentially what this does, it limits validator elections to the last block of each epoch. This means that you can verify any header in any order within an epoch, and allows you to download only the last header of each epoch. So if you want to sync from the Genesis block. So, and at 5-second block times and 1 epoch per day, this reduces the amount of data that a light client needs to download by a factor of 17,000. Sorry. Next, Plumo uses BLS signature aggregation to aggregate all of the signatures from each of the validators to a single constant size multi-signature. This reduces the block size by roughly 10 times, further improving the light client performance. And finally, Plumo uses SNARK proofs to compress the epoch syncing and BLS signature verification even more, which means that we've been able to reduce the amount of data needed for a transaction all the way down to a single 500 byte proof. So, returning to this idea of creating a bridge between a private CBDC network and a public blockchain like Celo, for example, these innovations, the epoch-based syncing, the BLS aggregation, and the use of SNARKs, means that Plumo is 100,000 times lighter than Bitcoin and 11 million times lighter than Ethereum. More importantly, it also means that bridges are now possible. So as central banks and industry stakeholders start to think about the idea of building bridges for CBDCs to other blockchains, both public and private, we will need to be vigilant about the data requirements for these bridges. Developing best practices and industry standards based on Plumo design of using epoch-based syncing, BLS signature aggregation, and the use of SNARKs may be a helpful place to start. So with that, I'd like to thank you for your time, and I'm happy to address any questions that you might have, and I look forward to further discussing this topic. So I'm gonna go ahead and stop sharing my screen. 1 second, let me just figure out how to do that. There we go. And I'll get back to, excellent. So I think we do have a few questions that I would like to address. So let me just pull these questions up. Okay, so the first question, how can the creation of technical standards help improve the interoperability of CBDC? This is a really important topic, and the idea of standards is particularly important when we're talking about interoperability issues. And you can kind of think about that like the internet. Back in the day, the internet, when it was first formed, you could see this this idea that perhaps it could be balkanized and people could, regulate certain parts of it and keep certain parts of it open. But there's been a number of great standards around the internet, especially with TCP/IP protocol, which basically allows for this open source design and allowing people to utilize that fabric and that architecture to build applications on top of it. So when thinking about CBDC, we need to sort of take a similar approach as we have with the internet. one of the things that we focused on in this presentation is this idea of how much data it requires to sync up with the blockchain and to then verify the state of the blockchain. So, central banks and their technology partners are going to need to think about, that process and think about how much data it's going to require for other entities to verify that the blockchain that they have is correct. One of the things that has always been foundational for the people working on Celo is, we wanted to really make sure that, this notion of data requirements was always very big for us, because the idea of financial inclusion was one of the things that we've been working very diligent towards. And when you think about people who perhaps live in remote villages in areas around the world, they may not have the latest smartphone, the latest iPhone, but many of them do have smartphones, but they don't have access to banks, whether that's because banks just aren't in the area, whether it's too expensive, et cetera. But they do have access to smartphones, but of course they might still have limited data availability. And so we really want to think about making sure that these transactions require as little data as possible, so that the user experience can be as fast as possible and as light as possible. So, thinking about the standards around that not only helps with interoperability between networks, but it also helps with the user experience and the operability within a network. Okay, so I think we'll go to the next question. I think we've answered that one. Yep. So question number 2. If CBDC is run on a private permission network and all participants are known and perhaps regulated, could you not just use a trusted bridge solution? This is a very good question. Certainly, you could use a trusted bridge solution if everybody is known. And that might be possible with a wholesale CBDC version, where when you think about in that version, it might be a central bank that issues the CBDC, and they only share that and make that CBDC accessible to commercial banks within their region. And so you have this very small network, and they all trust each other, and they can all then confirm the transactions. But where it then gets more tricky is that, even between, one country and another, there might not be that much trust. So when you think about like trade financing and things like that, if you actually wanted to use CBDC as part of a payment method, one country may not necessarily want to trust the other country that their blockchain is in fact correct. And so, they may not want to use a trusted version. Instead, they would probably prefer to do a trustless version, where they can actually look at the state of the chain, they can verify all the transactions, they can make sure that the money, is in fact valid and it's there. And so even in that sense, and even with wholesale versions, you would still probably want a trustless version, and especially for retail, right? So when people are using CBDC, and especially if it's a tokenized version of CBDC, you would definitely want to think about a trustless version, because you wouldn't have, for example, the account information. If there was an account-based CBDC, of course, you could have somebody act as an intermediary and check someone's account to make sure that the money was in fact there, and that it was enough to cover the expenses. But in a tokenized version, you need to just make sure that the actual token is in fact valid. And so in that sense, you really do want a trustless version. Okay, and I think the last question, does the central bank have to run their CBDC on the Celo blockchain to take advantage of the Plumo-like client? The short answer to that is no. Obviously the Celo blockchain has the ability to allow a central bank to run a CBDC on the Celo blockchain. That can be done in an open and decentralized manner. It can also be done in a private, permissioned, and centralized way as well. There are options there. You can even think about doing a synthetic version of a CBDC. And all those are sort of, I guess, a topic for another day that we'll definitely discuss on how you could build CBDC on Celo. But the point of this question here is simply that, Plumo is an open sourced design. So the Celo blockchain is all open source. So you can simply just use the code for yourself. You can also, the idea here is Plumo is helping to create this architecture and is helping to innovate technologies such as the epoch-based syncing, the BLS aggregation, and the use of snarks, and specifically the use of particular elliptic curves within a snark proof. And so if a CBDC decides to follow that lead and to create their architecture similar in a way that is similar to how Plumo is designed, and essentially make their architecture compliant with Plumo, then you can certainly take advantage of the ability to shrink down that data to a very, very small amount. So I think that concludes the questions. I hope you've enjoyed this brief discussion on interoperability and how it relates to CBDC, how it relates to the Celo blockchain. We look forward to any questions you have. We look forward to any further topics. We will certainly be having more topics to discuss later. I know one of them that I'm very passionate about is creating a synthetic version of CBDC. So that will definitely be another topic, but please reach out. Let us know if there's anything that we can provide as far as information. And also, as I mentioned earlier, for those of you that are far more technically inclined, want to really understand the math behind some of the stuff I talked about, please visit our Crowdcast page. And there are definitely a lot of presentations there. I know a colleague of mine just gave one today on interoperability, and specifically diving very deep into this use of snarks and how our epoch-based syncing works and our BLS aggregation. So I certainly would encourage you to check out all of those resources as well. With that, I thank you, and hopefully we will see you back here for another episode.